All right, now let's talk about how to solve the question number 2 for AP Physics C, Electricity and Magnetism 2023 free response questions. Okay, so here's number 2. Two horizontal parallel conducting rails are represented by distance L equals 0.4 meters. I refer to this distance. And a resistor of resistance R equals 0.3 ohm connects the rails. A horizontal ideal spring is located between the rails. The right end of the spring is free to move, and the left end is fixed in place. If we were to set up here, the spring can move this way. Okay. A conducting bar of mass 0.23 kilogram is placed on the rails and is in contact with the spring, which is initially compressed. Frictional forces and resistance of the bar and rails are negligible. At time t equals 0, the bar is released from rest and is pushed to the right by the spring. So the bar will start from here with a compression of the spring. And when we release the bar, the spring will push the bar to the right side. And when the spring is at the original length, its own length here, the bar and the spring will separate. However, because there's no friction force, etc., the bar will continue to move with a constant velocity going through, entering the magnetic field here, okay, starting here. And then because of the induction, so that time is T1, and because of the induction of this metal bar, there will be current in the metal bar, and that will cause the magnetic field to apply a magnetic force pointing to the left on the bar, try to slow it down. Okay, and then it will reduce its velocity, and then going through the second magnetic field region. Now, the second magnetic field region has the same magnitude of the magnetic field. However, the direction is reversed. So the cross sign here represents the magnetic field going into the page. Now the dot here will represent magnetic field going out of the page. Okay, so now we reverse the magnetic field. However, you will see that the magnetic force acting on the metal bar is still to the left. Okay, even if we change the direction of the magnetic field, we still have that left side direction. Now at time t4, that this instant, this position here, the metal bar enters the region where there's no magnetic field. Okay. Now we'll consider a time instant TB in between T2 and T3. So that refers to so here, let's see. Okay, so here is T1 and T2 is here. So T2 and T3 is between this region. Okay, so the first magnetic field region. On the diagram, on this diagram here, draw an arrow indicating the direction of the net force exerted on the bar at time TB. Okay, so first we need to figure out the current direction. So here's the induced current direction. Here's the metal bar, and the magnetic field is into the board. That's the first magnetic field going into the board or into the page. Now, if you think about this loop, the closed loop here, okay, so the flux through such a loop is increasing. It's increasing in magnitude, and such a flux is into the paper, into the page. So the direction here is into the page, right? So and it's increasing. So according to Lenz's law, the induced current will oppose such an increase of the flux. So the induced B will be out of the page. It will be this way, right? So now use right hand rule. You can determine the induced current direction. So the induced current direction would be counterclockwise. Meaning if I draw the current on the metal bar, it will be this way. So that's the I induced. It's counterclockwise. So now we're thinking about the magnetic force acting on this induced current. Okay, so the magnetic force on the induced current is given by I induced cross product ILB. Okay, and the B direction here is the original magnetic field. We call it the B1 already. So it's this B1 here. So now if you do IL cross B using right hand rule, the force direction is to the left. Okay, so that's why we should draw FB right to the left side, and that is the net force. So FB here is the net force, because the gravity and the normal force from the rails, they are both in the vertical direction and they cancel out. Okay, so the only net force here is the only force generated net force is the FB. Now question B, at time TB, the speed of the bar is V equals 2.5 meters per second. Now calculate the magnitude of the current in the bar at time TB. So for question B, we need to first calculate the induced EMF equals B1L times V. And let me see, B1 is 0.5. B1 is 0.5 and L is 0.4 meters. V is 2.5. So the induced EMF is about 1.67. Okay. So I don't actually have this number here, so let me calculate that real quick. So it's 0.5 times 0.4 times 2.5 equals 0.5 volt. Now I need to calculate the current. So the induced current is EMF over R 0.5 over the resistance is 0.3, so we have 1.67 amp. That's the answer for the question number 1. Question number 2, calculate the magnitude of the net force. So the net force is from this equation here. Okay, so we'll see they have 90-degree angle. So the cross product here introduces sine 90 degree equals 1, which equals 1. So it's I induced LB. I is 1.67, L is 0.4, B is 0.5. So that gives us the magnetic force 0.33 newtons. The direction is to the left. We already said that. Now question C. On the following axis, sketch a graph of the speed v of the bar as a function of time between t equals 0 and t equals t4. Okay, so now we know that from the from our previous discussion, we know the for the time instant between 0 and t1. So t1 is the instant when the spring and rod separate. Spring and the bar separates. Okay, so in this time interval, the only force acting on this metal bar here is the spring force, and the spring force will accelerate the metal bar. However, how do we draw that acceleration? How do I draw that velocity? So we need a velocity relation, right? So we know it's an oscillation here. It's a 1/4 of the harmonic oscillation, simple harmonic oscillation. So we can kind of write down the velocity relation using a sine function. So the V1 here represents the magnitude of the oscillation for the velocity, and then we should have sine omega t here, and omega here is square root the spring constant over mass, the mass of the rod. So you should kind of have that relation, and if you plug in the t here, let's say t equals 0, the velocity is 0. Okay, so that means that it starts from the 0 velocity from rest. Okay, so that's the maximum compression of the spring. And when we go to t1, the velocity should be maximum. Okay, so that's why we should draw for this part, we should draw a sine function starting from 0, ending with this t1 here. Okay, now after t1, you will do constant velocity motion before entering the magnetic field at t2. Okay, so t2 is the instant it enters the magnetic field number 1. So between these two time instant, V is actually V1 equals a constant. So we should draw a horizontal line. Okay. Now when it enters the magnetic field, we know we already did that calculation of the magnetic force. It will slow down the metal bar speed. Okay, with such a force here. But what we need here is not a specific number. It's a relation between the velocity and the time. So let's derive that. So between t2 and t3, the force acting on the metal bar is ILB, and I we know is BLV over R, the resistance R. Okay, so we have B square L square V over R. Okay, and that according to Newton's second law equals ma. So the acceleration a equals b squared L squared v over mr. Now, this a here should carry a negative sign because it will slow down the speed, so that equals dv dt. Okay, so we need to integrate this differential equation. So I need to separate the variables. dt goes to one side. So I'm going to move dt to the left side. So we have negative b squared L squared over mr dt. And the right side is 1 over v dv integral. Let's put it in the integration bounds. Right, t goes from t1, t2 to an instant t. And I also want to change this one to a variable t prime, right, because t now represents the upper bound. And I change here from v to v prime, becomes a variable. And then the integral here goes from v1 to v. Right? v1, remember, is this v here. Actually, let me label that v1. That's v1. So this integral on the left side, we have negative b squared L squared mr. Then t minus t2 equals, the right side is log, a log function, v over v1. Okay, so now let's rearrange these terms. Let's make an exponential here and then get v over v1. So v equals v1 times e to the negative b squared L squared over mr, and then t minus t2. So that's the relation we needed. So it's an exponentially decay function. So you should have an exponential decay like this. Okay, that's from this relation here. Now, how about between T3 and T4? Okay, so now we're going to enter the second magnetic field, B2, which is into the board. So let's look back at the previous, actually out of the board, sorry. It's out of the board. So B2 here is out of the page. Okay, so let's try to determine the force direction first. So the flux, okay, so at the beginning, the flux is still into the page, right? Because there's small area here has flux out of the page. Most of the area here is still into the page. So the total flux is still into the page. However, because of the cancellation, so this flux out of the page will cancel partly the flux into the page. So the flux is actually decreasing. So according to Lenz's law, the induced current, induced magnetic field will oppose this change, right? So the induced, B induced, is into the page to oppose the decrease of the flux. And then according to right-hand rule, in order to have such an induced B into the page, we should have a current using right-hand rule, okay? A current going downward. Or is clockwise. If you think about the whole loop here, so the metal bar here, now we have a current going downward. All right, so now according to the the right-hand rule for the force acting on the middle bar. So remember B now is in a region right out of the board. That's B2's direction. So IL cross B, that direction is to the left. So we should draw this FB2. Okay, so now you see, even if the magnetic field changes to the opposite direction, the force still to the left. And the previous expression still applies. So we still have a exponential decay. So let's go back to the previous picture. It's still decaying using this relation here. Okay, until time t4, and then after that, because there's no magnetic field, so the flux does not change anymore. So we're gonna have a straight line here. That's constant line. Now question D, now we're looking at the additional resistance here. Determine the total resistance R total of the closed circuit. So that's an easy one because we have two parallel resistors. So R total is R over 2, right? It's half the R. So we have 0.15 ohm. Now in the original scenario, the magnitude of the acceleration of the bar immediately after the bar enters the first uniform magnetic field is A original. In a new scenario, now is A new. So is A new greater than, less than, or equal to the A original? So let's look back at the acceleration that we solved earlier. So let's look at this equation here. Yeah, this equation here. So the acceleration is given by B square L square V over MR. Okay, and that's the original. Now A new, right, if I use the same equation here, similar equation here, I'll get MR over 2 instead. B square L square did not change, V doesn't change. So that means that the A new now doubles. Okay, so now let's look at question C. Describe a modification to M, B, or L that will result in a smaller induced potential difference across the original resistor immediately after the bar enters the first uniform magnetic field. Justify your answer. So we need to have a smaller induced EMF. So let's look at the expression that gives us the induced EMF, which is BLV, right? That's the induced EMF. So I can reduce B. So first way is reduce B, then E decreases, EMF decreases. The second way of changing the EMF would be L. So I want to reduce L, that will also reduce EMF. And M here doesn't matter. So if you have a mass, right, it can be any value of the mass of the bar, and it will not change this EMF. Okay, so this one is irrelevant. Okay, that's the second question solution for 2023 AP Physics C, Electricity and Magnetism. Free response question.